I started all this talking about the principle of least action, and I knew I'd come back to it soon. The reason is that I find something strange around it. Throughout the history of physics, this principle has always been absolute, and it has been applied to many kinds of problems. There comes a time, however, when it ceases to be entirely valid. In quantum mechanics, there you can no longer say that the particle or system follows the trajectory that makes action the least. The closest we retain from it is the powerful Feynman path integral formulation, but still is not the same. While in classical mechanics the principle provides the single trajectory between the points A and B, the new formulation gives a specific weight to each of the possible trajectories between them in spacetime. The contribution of all the weights results in the probability that the particle gets from A to B.
The most shocking thing about this modification is that most scientific community has interpreted it as an inherent property of nature and not as a limitation of the experimenter's knowledge about the system. But why this change? After all, either the particle arrives at B or it does not. When you find deviations between the different runs of the same experiment, one can always interpret, of course, that this deviation can from the fact that the repetition is not being exactly the same. But then you have to say what is not the same. And here you are working with supposedly fundamental components of nature, so it feels clumsy to think that something is changing inside them. From there came the idea of hidden variables. But what if what is really going on is that there is something in action that we have not taken into account in the way we calculate it?
On the other hand, why do we calculate the action between A and B? Is it that the history of our system ends there? What about the action between B and C, and between C and D? And what about what happened before A? Does the fact that the action is minimal between A and B imply that it will also be minimal between A and C, A and D, before A, and for all time?
Well, the truth is that under certain mathematical conditions of continuity and good behavior of the potentials, also the space-time you are working on, of course, then yes, this little piece of the trajectory determines it completely. But are we certain that our space-time is continuous like that?
In its origin, quantum mechanics was not about wave functions or probability distributions, and not about things that are at the same time in different places or states. It was about discrete steps in energy, about little leaps. So, what if the presence of those little leaps in the structure of our universe implies that action should be computed differently? I'm going to propose a little thought experiment. It is simply about thinking in a space-time of 2 plus 1 dimensions, but built in a grid, so that only the grid positions are valid. I am not saying with this that I believe that we live in a grid of little squares, but it will work well for what I want to show. This is a saying that we do when we solve numerically with a computer many physics problems, but I'm going to underline some properties that often comes as an important.
Let us suppose that we have this coordinated axis and a particle that from the origin at t equals 0 is launched with a given velocity. Let us also suppose that in this space there is a uniform gravitational field in a -y direction, so that the trajectories will be parabolas. Let us explore the cases in which the particle is launched in such a way that starting from the origin at t equals 0, it arrives at one of the points of this region, this square defined between positions 1 and 3 for both coordinates x and y, at t equals 1. If the space is continuous, then the particle can be launched to any point within the square, and whatever point is chosen, we will also know that for t equals 2, the particle will be in one of the points of this area, and for t equals 3, one of this, and for t equals 4, one of this, and so on. By considering a continuous space over the real numbers, then, for each point of the first square, we can assign a single point in each of the other regions. The number of targets available in the first square will be the same as in the second, third, and fourth, infinite, and they all with the same cardinality, that of the real numbers. Therefore, each point in region 1 for t equals 1, 2 for t equals 2, 3 or 4 corresponds to one and only one trajectory and is associated with only one point in each of the other regions. The trajectories would be contained in this envelope, and all points within it, whether we use Newton's laws or the principle of least action, are accessible. However, if we discretize by imposing our grid, there are now only a few specific points within the area corresponding to t equals 1 where the particle can go, and they are finite. If we develop the trajectories taking into account that they must forcibly fit the grid, with rounding as appropriate, and using a discrete version of Newton's laws, each of these points will correspond to another point in region 2, 3, and 4. In region 2, there are already more points, 25, than in region 1, where there are 9 only, so the assignment can no longer be bijective. Okay, in our initial area at t equals 1, we have 9 points of the discrete space. If we let them evolve inside the discrete version of Newton's laws, we will find 9 trajectories that do something like this. We can see that within the envelope of the trajectories there are now points that are inaccessible. Nonetheless, nothing prevents me from asking myself what the value of the action would be for a trajectory that passes through this point, and if, for the specific potential, that trajectory registers the minimum of the action. Then that should be the chosen trajectory since, strictly applied, the principle should explore all the points of space, discrete or continuous. It may not make a difference in this case, but if we set up situations in which the potential varies at different scales of space, then the quest for minimum action will lead us to trajectories that Newton's laws could not find.
I insist, this is just a silly example. My point is that if you accept that there is a minimal granularity in the base of nature and apply this action principle consequently, then you will come across deviations in your trajectories of a very particular size and surprisingly alike quantum fluctuations. They might seem random, but are indeed caused by the whole landscape of your potential. So, could it be that the least action principle remains as simple and powerful as it ever was?